my name is Alex Zhang and I am in Mr. Happ's Calculus BC class. This video will explain the topic of Maclaurin and Taylor series. When looking for power series representations for functions, there are many functions that can't be written in a form of 1 over 1 minus x. The general method for writing a power series for a function is called a Taylor series. Here is the Taylor series function, defined by f of x about x equals a. As you can see between the two functions, a Maclaurin series is just a Taylor series at a equals 0. The purpose of these power series is to find the approximation of a function. Assuming we can find f of 0, f prime of 0, and the second derivative at 0 for the original function, we can keep adding terms to the series for a more accurate approximation. The derivative of the function and the derivative of the approximation are equal at 0. For example, in an approximation with 3 terms, they are equal at x equals 0, have the same first derivative, and also the same second derivative. Eventually, with an infinite amount of terms, the approximation should look exactly like the original function. As you can see here, the approximation is better with more terms. First, let's find the Maclaurin series for the function cosine of x using the definition of a Maclaurin series. You first write out the derivatives. Let's do it up to the fourth. Plug each in for 0, then write it out based on the Maclaurin series formula. This can then be written as a series. The same process can be done for a Taylor series. Here are the general Maclaurin series formulas that you should definitely memorize and would save you a lot of time on something like the Maclaurin series for cosine of x. Let's try something more difficult. Let's find the Maclaurin series for x squared times arctan of x to the third. We already know, based on the general formulas, what arctan of x is. Let's write that out. If we want arctan of x cubed, replace x with x cubed in the formula. Now we have to multiply all of that by x squared. Just add the exponent of 2 to the x component of the sum, and you have your final answer. A common mistake occurs when people don't multiply out the exponents before adding on more exponents, and end up multiplying by more. We can also find the radius of convergence from this Maclaurin series. Using the ratio test, we write out the limit of n to infinity, replace n with n plus 1, and multiply it by its reciprocal. Then we can simplify. Also, a tip is to leave out negative 1. I didn't do it this time just to show. That's because the absolute value always makes it positive. Next, you can divide both top and bottom of 2n plus 1 divided by 2n plus 3 by n, and then you find the limit of infinity to that. You end up with x to the 6th power. The absolute value of x to the 6th is less than 1, and since the 6th root of 1 is 1, the radius of convergence is 1. Using these concepts, we can do another type of problem. Let's evaluate the indefinite integral of e to the x minus 1 all over x. First, let's write out the formula for e to the x. Next, to take away 1 from e to the x means taking 1 away from the entire e to the x series. After subtracting that from the entire series, the series becomes the sum starting from n equals 1 instead of n equals 0. We also need to divide the entire thing by x, so since we know that 1 over x is x to the negative 1 power, the x to the n becomes x to the n minus 1. Now we can finally integrate the whole thing. Using integration method, we add 1 to x to the n minus 1, then divide the entire thing by n. Let's also not forget plus c. There's our final answer. A tip to approach these types of problems is to always break it up into parts you know and can evaluate. In this problem, we knew what the series of e to the x was. Taking away 1 would just change the start point from n equals 0 to n equals 1. Finally, we knew 1 over x could be included into the series. Given what we know about series, we can also use this concept to find a limit. Let's do another problem. Let's use series to evaluate the limit of x to 0 of 1 minus cosine of x over 1 plus x minus e to the x. This looks sort of complicated, right? But we already know the formula for cosine of x and also e to the x. Let's write that out. Now we see that the numbers cancel out quite nicely. We can rewrite the limit with the series at the top and at the bottom of the fraction. Since we're trying to find a constant within all the x variables, it looks like both top and bottom share an x squared. Let's divide both top and bottom by x squared, and we end up with an answer of negative 1. In doing this type of problem, it's a good strategy to write out all the series in the limit. This will help you visualize what exponents you have and what you need to cancel out. And again, if you have trouble with where to start, it's always a good idea to start with what you know and solve it in parts. Next, let's go back to Taylor series. There's an amount of error for each term in the approximation, and the amount decreases for every term. Error for the nth Taylor polynomial is defined by f of x minus the nth Taylor polynomial equals the remainder. Lagrange error theorem bounds the error, telling us how closely the Taylor polynomial approximates the function. It's defined as if the Taylor series exists, the error is bounded by error is less than or equal to m, the maximum value, times the absolute value of x minus a to the n plus 1 power, over the factorial of n plus 1. M is a value satisfying f n plus 1 derivative of x is less than or equal to m between a and x. Let's try an example to explain this. For f of x equals sine of x and a equals pi over 6, find the fourth degree polynomial and estimate the accuracy of the approximation for 0 is less than or equal to x is less than or equal to pi over 3. For part A, let's start by listing derivatives up to the fourth, then plug in our a value, pi over 6. And to use in part B, let's write out the fifth derivative. Now we write out the polynomial using the values we already have. Also, make sure not to forget the factorials. Now for part B, we already know the Lagrange error formula, and yeah, it does look complicated, but essentially we can just break it down into parts and evaluate what we already know. In the formula, we can already plug in a with pi over 6. We're finding a fourth degree polynomial approximation, so n equals 4. We also know that m can equal the n plus 1 derivative of f of x, and that makes it the fifth derivative. So now we have our function. Now we use our bounds of 0 and pi over 3 to solve for the absolute value of x minus pi over 6 to the fifth power. We can manipulate the bounds to solve for it. And since we're trying to find the maximum value, pi over 6 to the fifth is our choice. Finally, since we already know the fifth derivative is cosine of x, we can use our bound 0 to pi over 3 to evaluate it. Plugging in 0 gives 1, and pi over 3 gives a number less than 1. So we know that 0 will provide us the greatest value. Now we have our final function, and it simplifies to an error of at most 0.000328. It's not too bad after you break it down. For extra practice, look to the worksheet attached. These problems will be more difficult, but you can apply the same concepts to solve it. Remember again to break things up into parts you know how to solve. Thanks for watching, and I hope this helped.